Now, this leads us into more of a better description as to what makes one atom different from another atom, or what makes one element different from another. All right, so let's talk about the atomic number, which is given the symbol Z. And the atomic number is very important, and all periodic tables will have, I've ever seen anyway, they'll all have the atomic number on it. So the atomic number for aluminum is number 13. And what that means is that all aluminum has 13 protons. Atomic number is literally just equal to the number of protons. All aluminum has 13 protons, and if you have an atom with 13 protons, it's aluminum. So the atomic number goes really well with the symbol, and again, the symbol is just a 1 or 2 letter representation for the atom. All right, every time you have aluminum, you've got 13 protons, and every time you have 13 protons in an atom, you will have aluminum. If you change the protons, the atomic number, you change the element itself. So Z, this atomic number, is literally a way to tell one type of atom from another. All right, if you have an atom with 14 protons, it's not aluminum anymore, it's going to be silicon. And if you have an atom with 12 protons, it's going to be magnesium, etc., etc. So you can look right now at a periodic table. If you don't have one out, you should get one out right now. But anyway, you can literally look at a periodic table and you can tell how many protons are in the different atoms, which is just cool. So uranium is 92, hydrogen is 1, sodium is 11, etc., etc. The atomic weight, which is the other thing on the periodic table, is going to be even more useful to us in the long run. But we kind of have to build up to it. So just bear with me right now on the atomic weight. But that other number is the atomic weight, and we'll talk about that more here in a little bit. All atoms of the same element have the same number of protons. So again, aluminum has 13 protons. 13 protons is always aluminum, etc., etc. This guy named Moseley was the first one who determined the atomic number in 1914. He used an X-ray technique, X-ray scattering, to figure these things out, which is kind of cool. All carbon atoms have 6 protons, and if you have an atom with 6 protons, it will be carbon. Same thing if aluminum will always have 13 protons. 13 protons in an atom will be aluminum, etc., etc. That's really important, and that's the way that people figure it out. Now, again, this number of protons in the atom is called the atomic number, and it's on all periodic tables. You can literally look by it. It's often above, sometimes to the left or right, etc., etc. So here's a question. What's the atomic number of oxygen? So first of all, you have to know on the periodic table where oxygen is, all right? It's in the upper right-hand corner, all right? Totally. And then you need to look at the whole number next to it to figure it out. Now, if you look at oxygen, there's an 8 and there's a 16, all right? Actually, the number is usually about 16. It depends on your periodic table. Often it'll say like 15.9994 or something like that. So you could say approximately 16 or 16. But guess what? Those aren't the atomic numbers. The atomic number is the small whole number. It's number 8. Oxygen is always number 8 on the periodic table. And again, that means oxygen has 8 protons. If you have an atom with 8 protons, it's going to be oxygen. All right. We'll talk more about the approximate 16 number later on. That's the atomic weight again. That'll come in useful later on, and we'll see where that comes from. In addition to the atomic number, which is number of protons, it's also nice to know the mass number. And mass number is given the symbol A. And mass number, which is usually in units of atomic mass units, that really small grams we saw earlier, mass number equals protons plus neutrons. So if you know the protons and the number of neutrons, you can find the mass number. One example of how this works is with boron. And boron will often have 5 neutrons with it. Now, if you look on the periodic table, boron is number 5. That's the atomic number. And if you have 5 protons, which is what that 5 means, plus 5 neutrons, which I'm just telling you right now, that's going to give you a mass number of 10. And this symbolism down here, which I call AZX sometimes, the top left-hand number is the mass number, 5 plus 5. The lower left-hand number is the atomic number, 5. And then this is just the symbol. All right, and because it's 5 protons, you're going to have the symbol B for boron. If it's boron, you'll have 5 protons. That's all the time. Over here on the right, you see some other ways that sometimes it's listed. Boron dash 10, the dash number, that number is the mass number of that particular species. And if you just see an upper left-hand number, for example, the 10 of this one, that's okay too. In the old days of Microsoft Word, it was difficult to do both a superscript and a subscript at the same time. Not impossible, but weird. So because boron is always number 5 on the periodic table, which is protons, a lot of times people will omit the mass or atomic number and only put in the mass number. Mass number is a little bit harder to find, we'll see. So all of these are ways to represent both the mass number and the atomic number. But the problem is that most elements come in different, I sometimes call it flavors, but that's not right. So let's call them different mass numbers, all right? And boron has 2 main mass numbers that are common, boron 10 and boron 11. Now, these are both boron atoms, and that means that both of them have an atomic number of 5. They're both going to have 5 protons. So if the number of protons is the same, remember you change that number and you change the element, you change it to like carbon if it was 6 or something. If the protons are the same, that means that the number of neutrons are different, and that's what makes an isotope. So an isotope is just an atom of the same element, same number of protons, but a different mass number, different number of neutrons. So we saw earlier boron 10, which was 10b, superscript 10b, 5 protons and 5 neutrons. Boron 11 would have 5 protons still, because again, if you change the protons, you change the element. And 6 neutrons. Now we got the 6, let's formalize this, by taking the mass number minus the atomic number, or protons and neutrons, which is what mass number is, minus protons. But there wasn't an explicit 6 in that. It wasn't like showing, we had to figure it out. If you hear about isotopes, it just means atoms of the same element, same number of protons, but different number of neutrons, different mass number. And all elements, I would argue, have multiple isotopes. Some are more abundant than others, but they're going to be important to us. How many neutrons in manganese 55? Okay, so neutrons are not something that you see in the representation of the element. So for example, in this problem, we see a 55. Well, that's not the number of neutrons. If you look at the periodic table, manganese is number 25, but that's not the number of neutrons either. So let's remember what these numbers are. 55 is the mass number. That's protons plus neutrons. And on the periodic table, the 25 you see for Mn, that's the number of protons. So if we take 55 minus 25, the protons and neutrons, which is 55, minus the number of protons, 25, we're going to get the answer C. This isotope of manganese has 30 neutrons. And again, we took the mass number, 55, subtracted 25, the atomic number from the periodic table, to get it. By the way, there is a manganese, Mn, and a magnesium, Mg. Magnesium is number 12, manganese is number 25. They sometimes sound familiar when you're learning this, so just FYI, they are different. Oh, joy of science. Here's an example of three isotopes that you may or may not have heard of, and these are fairly common. These are the three isotopes of hydrogen. Hydrogen has three main isotopes, and the first one is called protium, and that's like regular hydrogen. Now, look at the symbols on the left-hand side. Protons for hydrogen must be 1. So the lower left-hand number in all of those is 1 because it's hydrogen. Hydrogen always has 1 proton. But you can see the upper number, which is protons plus neutrons, goes from the top at 1 to the middle at 2 to the lower part at 3. So the top part, if it's a mass number of 1, that's protons plus neutrons. And if we subtract the protons, which is 1, that means this first one here has 0 neutrons. And that's called protium. Protium is by far the most common form of hydrogen. It's 99.9 some percent of all the hydrogen, stuff like that. Very, very common. When you drink water, most of the water, which has hydrogen in it, is protium. Now, the next one, though, is maybe one you've heard before, too. Now, this one has a mass number of 2. So 2 minus 1, that's 1 neutron. This is a heavier version of hydrogen, and the official name is deuterium. But the unofficial name is heavy hydrogen. Heavy hydrogen is sometimes used in nuclear experiments, or you hear about it and stuff like that. Check out the ice glass on the right-hand side. Normal ice, which is solid water up there, floats on the water. All right, no problem. The ice is less dense. If you have deuterium ice, which by the way would be kind of expensive, but it is kind of cool from a science perspective. But anyway, let's say you had D2O. So that's also H2O with hydrogen, but it's the deuterium version. It actually sinks. It's more massive. The density is greater. It sinks to the bottom. It's really, really cool. But anyway, I digress. Now, there is a third isotope of hydrogen called tritium, and this one with a mass number of 3 minus 1, it has 2 neutrons. This isotope is radioactive, and believe it or not, every time you take a drink of water, you've got some super, super, super small amount of tritium in the water, and it's normal. It's nothing to freak out about or anything. Our life is naturally acclimated to a little bit of radiation around us all the time. You get a little radiation when you go in an airplane, for example, so don't let that freak you out, but it is something that's around us a lot. If we had like 100% tritium, we would be in trouble as human beings, but fortunately it's very, very small. So anyway, hydrogen has 3 isotopes, and again, I would argue that all the elements have multiple isotopes, at least in some combination. There's lots of uses for isotopes. All right, there's lots of scary ones, which is all the nuclear energy and stuff, but this is a cool example. This is an example using something called technetium-99. Technetium is number 43 on the periodic table, and they can use it to create a type of a mellow gamma ray, and the gamma rays can actually help medical doctors see what's happening in your body, the soft tissues and stuff like that. Apparently, they use this up at OHSU here in Portland, but I haven't confirmed that. This is a mass spectrometer, kind of a diagram here, and this is how they figure out the isotopes. Now, in the lower right-hand corner is a graph, and notice here how there is a boron 10 and a boron 11, and to the right-hand side, there's a chlorine 35 and a chlorine 37. And how the mass spectrometer works is you put your sample in, and it gets vaporized, which means just really small particles. And then they also will usually shoot some kind of electrons at it, and the electrons end up making some very positive ions. This is an example with neon in this picture. And they can change the force of the magnet, like bigger, smaller, and stuff like that, and it separates out the different masses. So in the picture, there's a neon 20, a neon 22, and a neon 21. And the magnet is aligned just right so that the neon 21 is the only one that goes through the detector. So you end up with graphs that look like this, and we're also seeing them down below, which is kind of a cool thing. So think of this as like a super powerful bathroom bathroom scale for elements. All right. It's able to figure out like how much you have and stuff. Also, though, I want to point out for boron, notice here how the boron 10 is a much smaller amount than the boron 11. Boron 11 is a lot taller. All right. So if the boron 11 is considered 100, then the boron 10 there, it looks like, is about 25. So not all the isotopes are around us in equal amounts. And I already talked about how most of hydrogen is the protium, the simplest, a little bit of deuterium, and a super, super small amount of tritium. Most of the isotopes exist in multiple amounts, and we'll talk about that in a little bit.